Today we are going to discuss de Broglie hypothesis. Here we'll discuss de Broglie wavelength and how we have got the expression for de Broglie wavelength. What is the importance of that? And also, what was the basis of de Broglie hypothesis? Then we'll do expression for de Broglie wavelength for a particle like electron when it is accelerated under particular potential difference. So what is the expression for de Broglie wavelength there? We'll also discuss the importance and the details of the Germer and Davission experiment. So all these we'll discuss in today's discussion. De Broglie or de Broglie, the way you pronounce it, because it is pronounced in both ways, either de Broglie or de Broglie. De Broglie hypothesis was basically based once we got the expression and the details that light behaves like particle. Initially, it was believed that light has got the particle nature. It was given by Newton corpuscular theory there, and he has explained that light behaves like a particle. But then many phenomena were known after that, like the interference, diffraction, polarization, and other, which were shown by the waves. So then it was thought that light must have the wave nature. Huygens was the one who has proposed the wave theory. He has given the details of the and basis of the wave theory, and from his wave theory he was not only able to explain or prove the basic laws like laws of reflection and refraction, but he has also explained the phenomena like interference and diffraction there, which were shown only by the waves. So it was thought that light has got the wave nature. But then we come across the phenomena of photoelectric effect. Photoelectric effect is the phenomena which we cannot explain on the basis of wave theory. If we try to explain on the basis of wave theory, many of its properties and the observations we cannot explain. Wave theory has failed to explain photoelectric effect. And then again, it was believed that light has got particle nature. It was here the concept of the photon has been put forward, where photon we treat as the small packets of energy of light. So light can exist in the small packets there, which we call them as photons. Then it was thought that light has got the particle nature. Now by that time, there was also the expression given by Einstein for the mass energy equivalence relation, that mass and energy are equivalent there, using the formula E equals to mc square. Then de Broglie has basically proposed his hypothesis based on these two conditions and these two things what he has noticed. One was the mass and energy equivalence relation there, and also for the phenomena or the things that nature shows symmetry. In nature we find there is symmetry. Like if you consider that electric current produces magnetic effect, then we have the phenomena where magnetic effect or magnetic field can give electric current, that is the electromagnetic induction. If we say that electric current shows heating effect, that is the Joule's effect, then we have it's a symmetry where from heat we can generate electricity, that is the thermoelectricity. If we find that electric current produces chemical effect, then from chemical energy also we can get electrical current there. So here also he thought that if light has got particle nature, behaving like the small units there, so mass should also have the wave nature. So for that he has proposed his hypothesis. He said that every material particle is having the wave nature also. It was hypothesis because there was no experimental proof for that. So he has proposed his hypothesis that every particle or every material particle is possessing wave nature. And he said that the wavelength of such waves, it is related with the momentum of that, and he said that it is your h by mv. H is the Planck's constant, m is the mass, and v is the velocity. So this is lambda. Here we call it as the de Broglie wavelength. And these particles or the material particles for whom he has proposed that they are showing the wave nature. So the wave which is associated with that, for that he used the word like the matter waves. So they are called as the matter waves. So let's see how he has got these expression lambda equals to h by mv. Let us consider a photon having energy E and frequency nu there. Then from Planck's quantum theory, we have E given as h nu, where E is the energy associated with the photon and nu is its frequency there. So this, suppose I call it as equation 1. From Einstein mass energy relation or mass energy equivalence relation, we have E equals to mc square. Here it was a photon taken as a wave there. So electromagnetic wave having energy E, that is your h nu, and here nu is the frequency of the photon which is there, and this is from the particle nature. So E is equals to mc square, where we have considered that E is the energy associated with mass m. If you now equate equation 1 and 2, so from equation 1 and 2, what we find? Mc square is h nu, or it can be written as your mc square. Nu we can write c by lambda. So 1c we can cancel, and now we have lambda equals to h by mc. So this is your h by p, mass into speed. So this is your p. So de Broglie hypothesis was that wavelength is associated with momentum, which is given as your h by p. For material particle, this momentum p, we can write it as lambda equals to h by mv, where m will be mass of the material particle, which is moving with the velocity v. So this is the expression for de Broglie wavelength associated with a moving material particle. Now from this de Broglie relation, we can also conclude or get few more information there. Like here, first thing is there that it is the wavelength associated with a material particle. So a moving material particle is associated with a wave, and whose wavelength we have represented here by this relation. Now suppose here we assume that V is 0. If V is 0, then what we'll get? Lambda will be infinity. That means the wavelength will be infinite. It means there is no wave associated with a material particle at rest. So this one will be coming only, or it will get associated only with the material particle which are in motion. So we get de Broglie wavelength, or wavelength is associated with a particle in motion. Second thing was there is no charge in this particular expression. There is no charge associated. And if this is not having any charge associated there, that means it is not an electromagnetic wave, the wave which is produced here or which is associated here, because electromagnetic waves are associated with an accelerated charged particle. So that means the origin of these waves is not charged, or it is not of electromagnetic nature. And what we have seen, that moving mass particle or moving masses or the particles are only associated with such waves. A stationary one is not associated. So that means it must be associated there, as well as it is not same as that of the electromagnetic waves. So such waves were called as the matter waves. So this is the matter wave associated, and whose wavelength we have shown by this relation. De Broglie relation, what we take it as lambda equals to h by mv, and we say that it is associated with the material particles there which are moving with certain velocity v. Now this we do not observe in day-to-day life. The reason is that this Planck's constant value is very small. You know that this h is your 6.63 into 10 to the power minus 34. That much joules second. So now if you consider the objects which we come across in day-to-day life, suppose you take a ball or take a stone which is thrown with particular velocity, here you'll find that the mass of them and the velocity with which they are moving, that one will give you very small value of this lambda. Lambda will be very small, and it will be so small because even if you suppose consider m to be of 1 kg, in that case velocity, here we suppose take 100 meter per second or 200 meter per second, is still this term lambda which you will get, that will be very, very small. Like if this term h divided by 10 to the power 2 if I am taking, in that case this one will be very small, 10 to the power minus 36 meter it will be there. That is the wavelength. So that is why in day-to-day life we do not observe this. But whenever you take particles like the electrons there, which are moving there in the particular orbit there, in that case or in any other case, if you consider the small particles, the small mass particles like the electrons, in that case due to their small mass there and the velocity with which they are moving, there we may get this wavelength which will be there, which we can observe properly. So that is why we notice that one more prominently there, or experimentally we can measure that one for the small particles like the electrons and other, because they move there so that at such high velocity and they have the sufficient momentum because their mass is also very small. So in that case what happens there, this particular denominator will have such a value that this lambda will be in a measurable quantity. Let's now take de Broglie wavelength associated with an electron. Suppose we assume that we have an electron having charge E, which is accelerated under a potential difference V. So in that case, the energy possessed by this electron, it will be given as your E into V. So this is the energy possessed by accelerated electron. Now suppose we assume that m is its mass and v is the velocity acquired by it. So this energy which is acquired by the electron will be in the form of its kinetic energy. So we can write this one as half mv square. This v we are using for the velocity of the electron. So these two will be equals, because whatever will be the energy gained by the electron, it will appear in the form of its kinetic energy. So we can write this expression, or we can write v equals to 2ev by m square root. This is the expression for the velocity of the electron. Now, if we take de Broglie relation, So from de Broglie's relation, what we get? Lambda equals to h by mv. So for v, we'll substitute this one. So it is your h by m and root over 2ev by m. This will be equals to h by root over 2mev. So this is the expression for de Broglie wavelength, lambda equals to root over 2mev. So here you can see that this is the Planck's constant h, m is the mass of the electron, E is the charge on the electron, and this capital V is the potential difference under which that electron have been accelerated. So this gives the de Broglie wavelength there. Now you'll find here one more thing, that h, m, E, all these are constant. So it means this particular term, that is your h by root over 2me, this is a constant, and now it is your root over v. This particular term value, if you substitute, you will get an expression 12.27 root over v, that much angstrom. So lambda you can use there as 12.27 by root over v angstrom. This formula you can directly use for any numerical or any problem there, where for the electron its wavelength relation is asked at different potential difference there. So you can use this expression. Like if it is said that the potential have been increased by 4 times, so how the de Broglie wavelength will be associated? So it is 1 by root over v there. So in that case it is root over 4 times, so it is 1 by 2 times, that means it will become half there. So that is how you can relate. One more thing you can notice, that this E into V, this is the energy acquired, that will be in the form of the kinetic energy. So in some expressions you can also use this one as h by root over 2m into k, where k we are taking as the kinetic energy or the energy there. This k is your E into V. So at cases there where the energy is already given there, in that case you can use this particular relation there. This is the experimental setup of Germer and Davission experiment there. Basically they have performed experiment to detect the wave associated with moving particles like the electrons. So they have just tried to see, is there any wave associated with the material particle or not. And of course, if they have found that there is a wave associated, that has also proved this de Broglie hypothesis there, or they have supplemented that one, and they have said that it is true. So let's see the experimental setup of this Germer and Davission experiment. There they have a small filament here which is heated with the low tension there, that means small batteries there, or small voltage with which we can pass electric current. A filament will get heated, and there is a cathode there, that is one more plate is there. Once the filament is heating that, the electrons will get emitted there, and these emitted electrons, they will basically, if suppose nothing is there, in that case they will move in all possible directions there. So what we do, we use a cylindrical anode there, and this is connected to a high tension, and it is a variable one. That means depending upon our requirement, we change the potential difference between the two. Due to this cylindrical anode, there will be a beam of electrons coming out of this one, because that one will concentrate the electrons there. They will be moving along its axis there, and they will come out with particular velocity. They are allowed to strike a nickel crystal there. So they strike a nickel crystal there, and then the beam which gets diffracted, they are detected by this movable collector there, or detector unit you can say. This is the scale. That means we basically move this one collector and we try to see where we get the maximum intensity there of the diffracted beam. And this is basically connected to a galvanometer, from where we can detect how much is the current flowing there. The moment the current is maximum, definitely there it will be indicating the intensity is also maximum there. So this is how we measure that one, and we basically move it to test and check where we are getting the maximum intensity, and at different angles also what is that particular intensity. So we basically plot graph for intensity at different angle there when it is getting turned, and at different operating voltage. This entire apparatus is kept in an evacuated chamber there, and it is observed. Now what we find, that when the voltage, this oscillating voltage, is varied from 44 volt to 68 volt, then we find appreciable change there in the pattern of the intensity. So if you just observe that one, we find at a particular voltage there is a sharp peak. At 54 volt there is a sharp peak there. So let's just see how we get that one, because if suppose it is going at different oscillating voltage and we are measuring its intensity at the different positions there, we find that at a particular angle there, the intensity has a higher value. But at a particular voltage of 54 volt, there is a sharp peak. If you plot the nature of the intensity at the different operating voltage there, or oscillating voltage there, in that, and the different scattering angle, in that case we get nature that at 44 volt it is broad, at 48 it starts concentrating, then at 54 volt it has a sharp peak there. This sharp peak is indicating that there must be waves superimposing constructively there, and there is the maxima which is being observed. And this happens when the scattering angle is 50 degree there. This angle is your 50 degree. And at other voltage, that means if you increase beyond 54, again it will start getting broader there, and at 68 again it will become as broad as it was earlier there. So only at particular voltage of say 54 volt, it is giving a very sharp peak there. We have of course shown some representative voltage. Of course it is observed there, say for 44 to 68 volt range there, because there only we find the appreciable change in the intensity pattern there. So we find it there having max sharp peak at 54 volt, and the scattering angle is your 50 degree. Now here, if you consider this particular case here, now here it is theta, this is your phi, that is the scattering angle there. So theta plus phi plus theta, this is your 180 degree, or 2 theta will be equals to 180 minus phi, and how much we have taken this 50 degree there, so it will be equals to 180 minus 50, 130 degree, that is 2 theta, or theta will be equals to 65 degree. So this theta is basically your glancing angle. So the glancing angle will become 65 degree. Now if you consider from Bragg's law, it is your 2d sine theta equals to n lambda, and for first order diffraction, if you consider, in that case n will take it as 1. This d is the interatomic spacing or separation. So for nickel crystal, because we have used here nickel crystal there. So for nickel crystal, this value of D is your 0.914 angstrom. So if you substitute that in the formula, 2D sine theta equals to n lambda, we get 2 into 0.914 angstrom into sine 65 degree. That is your 1 into lambda. N is your 1 here. So lambda value, we get it as your 1.65 angstrom. This is the wavelength of the wave shown by the electron there, and it is measured experimentally. Now, if you consider from the de Broglie relation for the electron, which is accelerated under a potential difference V, the formula was your lambda equals to h by root over 2 MeV, or 12.27 by root over 54 volt, because at 54 volt we are getting this sharp peak there. So that if you substitute, it will give you 1.66 angstrom. So lambda is your 1.66 angstrom. So theoretically we expect the wavelength to be 1.66 angstrom. Experimentally we have observed it as 1.65, which is in close agreement between the experimental and the theoretical values there. So this proves that there is definitely a wave associated with the electron, and that we have measured here. So this also confirms the de Broglie hypothesis, that there is a wave associated with the material particles there. Remember one more thing. Here we are observing this diffraction there. We have taken the electron beam, and this one is showing diffraction. Diffraction is a wave phenomena. So if it is showing diffraction there, that means also this is indicating that it has behaved like a wave. That is why you have been able to get their diffraction pattern, and that diffraction pattern's intensity variation or maxima we have obtained. So there is a wave associated with the electron, and that also proves your de Broglie hypothesis. So this is all there in this chapter. That is the de Broglie hypothesis, its applications, and its derivation there, and experimental proof also to supplement de Broglie's hypothesis.